A truck starts from rest with a constant acceleration, until it reaches a speed of 30 meters per second, 10 seconds later. It then maintains a speed of 30 meters per second, for the next 90 meters. The driver then slows down at a constant rate, stopping 270 meters from the starting point. Sketch the displacement, velocity, and acceleration of the truck versus time as it travels 270 meters, from its starting position. We can draw a timeline with 3 intervals, as shown here. The first statement about the truck describes the first interval. A truck starts from rest with a constant acceleration, until it reaches a speed of 30 meters per second. 10 seconds later. The second statement describes the second interval. The truck then maintains a speed of 30 meters per second for the next 90 meters. Then the third statement corresponds to the third interval. The driver then slows down at a constant rate, stopping 270 meters from the starting point. Since the acceleration is discontinuous between each of the 3 time periods, we will break the problem into 3 parts. In part 1 we will find x1 and plot x, v, and a over the first interval. In part 2 we'll find the time t2 and also plot the response variables. And finally in part 3 we will find the time t3 and also plot the response variables. In part 1, we would like to find the value of x1 and make plots of velocity, acceleration, and displacement versus time. We are given that the time interval is between 0 and 10 seconds. And we are given that the velocity is a straight line between 0 and 30. The equation of the line is therefore, v1 is equal to v0, plus a times t. Acceleration is the change in velocity over the time interval, and is equal to v1 minus v0, over t1 minus t0, which is equal to 30 minus 0 over 10 minus 0, which gives us a constant acceleration of 3 meters per second squared. Now we can write our displacement equation. X at time t is equal to x at time 0 plus the integral from 0 to t of v dt. This is equal to x0 plus v0 times t plus 1/2 of a times t squared. Using this equation, x at time 10 is equal to 0 plus 0 times 10 plus 1/2 times 3 times 10 squared, which is equal to 150 meters. Similarly, x at time 1 is equal to 1.5. X at time 2 is equal to 6. X at time 3 is 13.5. X at time 4 is 24. X at time 5 is 37.5. X at time 6 is 54. X at time 7 is 73.5. X at time 8 is 96. And x at time 9 is equal to 121.5. In part 1, we plotted the response variables for the time interval from 0 to 10 seconds. Here in part 2, the time interval is from t1 equals 10 seconds, to some value t2, which we would like to determine. And after that we will plot the response variables for this interval. We are given that the velocity is constant at 30 meters per second. And therefore the acceleration is 0. We found from part 1, that x1 is equal to 150 meters. And we are given that the difference in x for this interval, is 90 meters. Which means that x2 is equal to 90 plus x1, which equals 240 meters. Velocity is the change in displacement over time interval, which is equal to x2 minus x1 over t2 minus t1. Rearranging the terms, we get t2 is equal to x2 minus x1 over v, plus t1. Thus t2 is equal to 90 over 30 plus 10, which is equal to 13 seconds. On our displacement versus time graph, we can now plot point t1 equals 10, x1 equals 150, and t2 equals 13, x2 equals 240, and draw a straight line between them. In part 1, we plotted the response variables for the time interval from 0 to 10 seconds. And in part 2, we plotted the response variables for the time interval from 10 to 13 seconds. Now, here in part 3, the time interval is from t2 equals 13 seconds, to some value t3, which we would like to determine. After which, we will plot the response variables for this interval. We are given that the velocity is a straight line between 30 and 0. And we are given that x2 is equal to 240, and x3 is equal to 270. According to the velocity equation, the velocity at time t is equal to v2 plus a times t minus t2. According to the displacement equation, x at time t is equal to the integral from t2 to t of v at time t dt. Substituting v at time t into the displacement equation and taking the integral, we get x at time t is equal to x2 plus v2 times t minus t2 plus 1/2 of a times t minus t2 squared. If we substitute t3 for t in this equation, we get x at time t3 is equal to x2 plus v2 times t3 minus t2 plus 1/2 a times t3 minus t2 squared. The acceleration is equal to the change in velocity over the time interval, which is equal to v3 minus v2 over t3 minus t2. Let's substitute the acceleration in the above formula and rearrange the terms of the equation to get t3 is equal to 2 times x3 minus x2 over v2 plus v3 plus t2, which is equal to 2 times 270 minus 240 over 30 plus 0 plus 13, which is equal to 15 seconds. So we have just determined that the time interval goes from 13 to 15 seconds. Now we can go back and find the acceleration. The acceleration, a, is equal to 0 minus 30 over 15 minus 13, which equals negative 15. Now let's plot displacement versus time. Our first point is at t equals 30, x 240. Our ending point for the interval is at t equals 15, x equals 270. Let's find 3 more points in between. Using our displacement equation, x at time 13.5 is equal to 240 plus 30 times 13.5 minus 13 plus 1/2 negative 15 times 13.5 minus 13 squared, which is equal to 253.125. Similarly, x at time 14 is equal to 262.5. And x at time 14.5 is equal to 268.125. Two points A and B are 200 meters apart. A racing car moving with constant acceleration covers the distance between the 2 points in 2 seconds. When it passes point B, its speed is 55 meters per second. Calculate the speed at point A. And calculate its acceleration. In this example it is given that points A and B are 200 meters apart. So if we let x0 represent the position of the car at point A, and x1 represent the position of the car at point B, then x1 minus x0 is equal to 200. We are also given that the car takes 2 seconds to travel from point A to point B, so we set t equals 2. And we are given that the velocity, v1, at point B, is 55 meters per second. We would like to find the speed, v0 at point A, and the acceleration of the car, which we have been told is constant. First, to find the speed at point A, we use the equation. Velocity at point B, v1, is equal to the velocity at point A, v0, plus the integral from 0 to t, of a dt. Because the acceleration is constant, the integral is simply a times t. And so we have v1 is equal to v0, plus a times t. Which can be rewritten as, a is equal to v1 minus v0, over t. We also know that the displacement at point B, x1, is equal to the displacement at point A, x0, plus the integral from 0 to t, of v dt. This is equal to x0, plus v0 times t, plus 1/2 a times t squared. Now let's substitute a into the equation. We can rearrange the terms to give the equation, v0, is equal to 2 times x1, minus x0, over t, minus v1. Now substituting the values of our inputs into the equation, we get v0 is equal to 2 times 200 divided by 2 minus 55, which gives a velocity of 45 meters per second. Next we can go back and use our acceleration equation. A is equal to 55 minus 45 over 2, which gives a constant acceleration of 5 meters per second squared.